Hello and welcome to Intermediate Algebra here at Bay College, our online lectures. Today we're going to look at section 6.3. This is going to be split into two videos. The first one is going to deal with adding and subtracting radicals and multiplying radicals. And the second video will deal with division of radicals. And sometimes when we do that we have an additional operation. Sometimes we have to rationalize a denominator, but we'll get to that in the second part of this section. The key to adding and subtracting radicals is essentially identifying what are our like terms. Now, we've worked with like terms before. They have to have the same variables to the same powers before we can add or subtract their coefficients. Now, if we look at these three examples here, if we ignore the radical for a moment, we see ax and bx. And if that's the case, well, ax and bx, I could do something with those if I were adding or subtracting. Well, now we have this radical expression. We have to identify two things, and that's the index has to be the same, and the radicand, what's under this radical, also has to be the same, just like terms. It has to be the same variables to the same powers. And if we look at these first two examples here, we have ax and bx. Yes, those are the same. We have the nth root. They have the same index, y squared z. So in every aspect, these are the same, so we would consider them to be like terms. Now, if we look at this example, well, if we didn't even consider the radical, we'd see this doesn't even have an x on the outside. And that's another thing we have to watch out for, is what's on the outside. Because this would not be a like term solely because it doesn't have an x out here. But if it did have an x and we were going to consider the radical as well, we notice the index is different. It's some other letter here or some other number if we were looking at an example. And the radicand here, we have yz squared. Well, the y squared and the z are different here. Okay? So this is not a like term, so we couldn't do anything with it. So let's look at an example we've seen many times before. You know, we've worked with like terms. So we have negative 2x plus 5x. We have minus 2 of these plus 5 of these. They're the same. So we can do this operation. 5x's minus 2x's is 3x's. Similarly, if we look at this example, well, these have radicands. We can treat these just like the variables in the previous one here. We have negative 2 square roots of 2, and we're going to add 5 square roots of 2. Since these are square roots, they have the same index, and what's the radicand for both of these is 2. So they are like terms. I can say negative 2 square roots of 2 plus 5 square roots of 2 are 3 square roots of 2. You notice, very similar. And that's how we treat these. So let's go over here and look at an example. I have the negative square root of 5 plus 4 square root of 5. Well, we see they're both square roots of 5, so these are like terms. How many of these do I have? A negative 1. How many of these do I have? A positive 4. So I have 4 minus 1, and I get 3 square root of 5. All right, not much work to be shown there. But sometimes when we deal with radicals, we can see, hey, those don't look the same. They may have the same index, but what's under the radicand is not the same. Well, sometimes we have to simplify our radicals, as we've seen in the previous section. So let's go ahead and simplify this the best we can. Well, I look at 27 and I recognize it as 3 cubed, or I can factor it down to 3 and 9. Well, 9 is a perfect square. I can take the square root of that, and I'd have 3 with the square root of 3 remaining. So I've just simplified the radical. Same thing here. I see, well, 75, well, let's factor that down. It's 25 times 3. If I had 3/4, I'd have 75 cents, right? Now, 25 I recognize as a perfect square, so I can say square root of 25 is 5, with a remainder under that radical of that 3. That factor of 3 would remain. Now, once we've simplified them, hey, we can identify this. They're both square roots of 3. So now we can do this math. 3 square roots of 3 minus 5 square roots of 3 is negative 2 square roots of 3. All right, the next example, we have the square root of 2 and the cube root of 2. We're actually done here. There's nothing more we can do because their indexes are different. They may have the same radicand, which they must to be like terms, but they also need to have the same index. This is a 2 and that's a 3. So in this case, this is as far as we can go. These aren't like terms. We can do nothing when it comes to addition and subtraction if they're not like terms. All right, so let's move to this example. They're getting a little bit more complex. And we see, well, we're dealing with cube roots. This one doesn't have any variable out here. It's just the coefficient of 2. This one has an a. So we might think, hey, these aren't like terms, but we must simplify any radicals first. If I look at this one, I notice that the power of this variable is higher than my index, so there is some simplifying I can do. I have 4 factors of a, and I want to take out 3 at a time, right? That's what a cube root is. How many factors are being multiplied together? So essentially I can say 3 goes into 4 one time, so 1 of the a's comes out. With a remainder of 1, 1 of the a's remain. So 2a cubed root of 3a. Now let's simplify this one. Well, we have an a out here and an a in there, and obviously this power is 1, so it's less than 3, so we don't have to simplify that. But what is 81? Well, I know 81 is a perfect square, but I also recognize it as a perfect 4th power number, 3 to the 4th. So I can say, hey, 3 goes into 4 once, so I can bring one of those 3 outs. Well, if we recall, if there's a coefficient out here and we bring out another factor, well, their factors have to be multiplied. So I'm going to multiply the 3 I'm pulling out by 3 to get 9. And again, just to make sure we got this, 3 goes into 4 one time with a remainder of 1. 1 has to remain under the radical. That 1 factor of 3 has to remain. And if we look at this, we see, okay, we have an a outside, we have the cube root of 3a for both cases here. So now they're like terms. Just by simplifying them, now we can combine the terms just by looking at their coefficients. 2 of these minus 9 of these is going to give me negative 7 of these a cubed roots of 3a. So sometimes they can get kind of complicated and we got to work our way through them, but we got to just take our time and practice. We'll eventually get it down pat. Now let's look at something a little bit more complicated here. We have 3 square root of 7 minus cubed root of x plus 4 square root of 7 minus 3 cubed root of x. Well, here we have 2 different radicals. We identify these aren't like terms, but these are like terms. These are both square roots of 7. I have 3 of them. I'm going to add 4 of them. So I get 7 square roots of 7. And if we look at this, minus the cubed root of x, minus 3 more of the cubed root of x, well, we're subtracting both of these, so we're going to combine these negatives here to negative 4 cubed roots of x. They both had the cubed root, and they both had an x as the radicand. So we can simplify some polynomial-like expressions by combining them as like terms. All right. So now, hopefully that makes sense to you. We're going to move on to multiplying radicals. And just like this had followed similar rules when we worked with polynomials and like terms and things of that nature, we're going to see multiplying radicals basically built on what we already know. If you had something like this, basically we have a binomial times something else here, we're going to use the distributive property. So I'm just going to distribute this to each factor, or each term, excuse me. Negative 2 times 2x is negative 4x, and negative 2 times 5y is negative 10y. Well, when it comes to radicals, we can treat them the exact same way. I'm just going to use the distributive property and distribute this to each of these terms. The square root of 2 times the square root of 2x. And if we recall from previous sections, if they have the same index, we can just do this multiplication under that radical. So I have the square root of 2 times 2x is the square root of 4x. And the square root of 2 times the square root of 5x, since they're both square roots, I can do that operation, the square root of 10x. Now, one thing we have to keep in mind of radicals is we always have to simplify them. And I recognize that 4 as a perfect square. Since we're dealing with square roots, I can say the square root of 4 is 2, so I have 2 square roots of x plus square root of 10x. 10 is the factors of 2 and 5, obviously, right? We multiply those. So it's not going to simplify. We don't have any repeated factors. So that's it. And if we look at this, 2 square root of x plus the square root of 10x, it's kind of similar. We had that 4x there before, and we had the 10y. Well, here we have the 10x, but now we just introduced the radical. And one of them we had to simplify. All right, let's move on to some more examples here. This looks just like the previous one, but we have some square roots and some variables and some numbers. We're just going to use the distributive property. The square root of 5y times the square root of y would give me the square root of 5y squared. The the factors all under the same radical because they got the same index. And I do the same thing to that term. The square root of 5y times the square root of 5 is going to give me the square root of 25y. And now we just have to simplify this. Well, I see I have two factors of y. I'm taking the square root, so 2 goes into 2 once with none remaining, so 1 will come out and none will remain. Just that factor of 5 that I couldn't do anything with. And we look at this, we have the square root of 25. It's perfect square, so we're going to take that out. And only one factor of y. And we can see these are not like terms, right? The y's on the outside, and the 5's on the inside. The 5's on the outside, and the y's on the inside. They're not like terms because what's under the radicand is different. Now what if we had something like this? Well, if the distributive property works, we're just going to use that special type of distributive property. Essentially, we have two binomials, right? 2 terms here times 2 terms there. We can use the process called FOIL. So I'm just going to FOIL this out. The first term's 8 square root of x times 4 square root of x is going to give me 32 square roots of x squared. Now hopefully you followed that. 8 times 4, we just multiply their coefficients. We have square root of x times the square root of x. We can multiply those x's together to get that. We'll simplify that shortly. And then we can do the inner terms. Y times 4 square root of y is just 4y square root of x. I may have misspoken and said y, but that's an x. So that's what we get. These are not like terms, so we get what we get, right? Nothing really multiplied together, so we just put them together as factors. And then we can do the outer terms, 8 square root of x times a negative 1. Well, that one's easy enough, right? Just gives us negative 8 square root of x. And then the last terms, when we FOIL, y times negative 1 is negative y. Now, we always want to combine any like terms and simplify if possible. So we can see, I can simplify that. That's going to give me 32, the square root of something squared, right? That x value, plus 4y square root of x minus 8 square root of x minus y. And this is actually where we're done because there are no other like terms here. This one just has an x with no radical. These two both have the square root of x, but this one also has a y. This one doesn't. They're not like terms, and that's just y by itself. So we're going to stop right there. And just to kind of maybe clarify the final answer, I'll put that around it so you can see when we FOIL this out, these are the terms that we get. All right, this one here, a common mistake that students do is just square this and square that. Well, that's not the case because this needs to be FOILed just like this one because it's saying these two terms times itself. One way to keep track of that is to maybe rewrite it. Square root of 2 plus x is going to be multiplied by itself, the square root of 2 plus x. And you can see you need to FOIL that out. You can't just square this and you can't just square that. It's illegal math. So if we FOIL this out, we're going to get the square root of 2 times the square root of 2. And I'm going to kind of skip a little step there. Well, I know I'm squaring the square root of 2, so that just gives me 2. And then the outer term would be the square root of 2 times x. So I just put that x on the outside there. And the inner term or outer term, whichever way we went there, x times the square root of 2 is x square root of 2. And then x times x is x squared. So that's the terms we get in the FOILing process. And we see, hey, we have some like terms. X square root of 2 plus x square root of 2 are 2 x's square roots of 2, and those are our only like terms. So the final answer is 2 plus 2x square root of 2 plus x squared. And we can see that's actually a trinomial. We could put it in descending order, x squared plus 2x square root of 2 plus 2, but that's fine. We'll just leave it right there. No more like terms. We've done all we can do here. All right. Now this one, a little bit different because we have a binomial, essentially, times a trinomial. Now, the acronym of FOIL doesn't work here, so we just have to essentially use the distributive property. So I'm going to distribute this to the first term, cubed root of 3x times the cubed root of 2x. Well, since they have the same index, I can actually do that multiplication under the radical. So I'm going to get the cubed root of 3x times 2x is 6x squared. And then I'm going to multiply that to the second term here. Negative 3x's times these, well, since this doesn't have a radical, it's essentially just write out the factors. 3 times x times cubed root of 3x. We are multiplying them. And then multiply this by the last term. Now I use these arrows so I don't get lost in my work. I want to make sure I multiply every term by this one and then every term by that one. So finally the last is just minus 1 times that. Just changes the sign because it's a minus 1. And then we have to multiply all the terms of this by this term. So 3 times the cubed root of 2x, and 3 times negative 3x is negative 9x, and 3 times negative 1 is negative 3. Now we just want to check and make sure, do I have any like terms here? Well, this is a cubed root of 6x squared. I can't simplify that any further. This is less than the index, so it's fine, and this is only the factors of 2 and 3. Can't simplify this. We might, for a moment, say, hey, are these like terms because we have the same index and same radicand, but they're not like terms because this one has an x on the outside. This one does not. This is the cubed root of 2x, which no other cubed roots of 2x. And we just have negative 9x and negative 3. So there are no like terms when we multiply this out. This is actually as far as we can go. That's the answer. We just used the distributive property and checked to see if we could combine anything. Now this one here, this next example, is like the other one where we had a binomial squared. Sometimes this can look confusing, but this radical is actually a single term, even though there's addition or subtraction in there. So what we're going to do is we're just going to FOIL it out. We're going to rewrite it x minus 6 minus 7 times itself, which is the square root of x minus 6 minus 7. And we can use FOIL. And this is one reason why sometimes I move away from FOIL and I use my little arrow property. The square root of x minus 6 times the square root of x minus 6. I'm squaring the square root. So it's going to give me x minus 6. Right? That value times itself. That's what this is asking us. And then this times negative 7 is just negative 7 times the square root of x minus 6. And if we do this, we got negative 7 times the square root of x minus 6. And negative 7 times negative 7 is a positive 49. Now we have to combine like terms. Well, there is only this one x term by itself. No radical or anything. There's just an x. We have the number negative 6, and we have a number positive 49. Let's combine those together. And I'm just going to write it back here. We're going to have positive 43 if I combine those two numbers. Now, if we look at this, negative 7 of these square root of x minus 6, negative 7 of square root of x minus 6. So we can see, hey, we have negative 7 of these and negative 7 of these. We have minus 14 of these square roots of x minus 6. So this is actually the final answer. And if you think about what we did when we squared that binomial previously, we ended up with a trinomial. Well, if you think of this, we have 3 terms, trinomial, right, tri, telling us that we have 3 terms. So we combine our like terms, and you can see that's as far as we can go. Don't make the mistake of thinking that this is still a separate term, because once we eliminated the radical by squaring it, we could actually combine it with something else here, that number. All right? So this has been video 1 of section 6.3. 6.3 part 2 will actually deal with dividing radical expressions and rationalizing their denominators. Thank you.